Okay, so I think we can start again, this time with press present. So, welcome back everyone. So far, we've discussed exclusively thermal production mechanisms, in the sense that these were dark matter production mechanisms of dark matter particles being produced out of the thermal bath. And then, as I stressed, it's a bit of terminology, whether you refer to it as a thermal production or non-thermal production. So basically, the most often used terminology means that, when you use non-thermal production, you just mean that the resulting phase-space distribution of dark matter is not thermal. So like in freeze-in production, for example. So now we will turn to really fully non-thermal production mechanisms that have nothing to do with the thermal bath, the plasma. And just as a starting point to put things in context, we can ask a simple question. So how light can dark matter actually be? And we've sort of every now and then addressed this already when talking about various production mechanisms. And we've noticed, for example, that when you have a fully thermal production mechanism, the really freeze out or something, so dark matter particles that have been fully thermalized in the early universe, then there's an absolute limit that dark matter must be heavier than a few MeV. So this is, if it's smaller, it's excluded for fully thermalized dark matter. So why is that? Because then in the early universe, these particles would just be relativistic, so they would contribute to the energy density of the universe, drive the expansion, and then at this mass scale get into conflict with BBN observations. So it's basically a constraint on the effective number of relativistic degrees of freedom during BBN for fully by BBN observations. Okay, so then we've also talked about dark matter produced from the thermal bath. And then dark matter can be lighter, because we basically don't produce dark matter in the full, the phase-space density or the number density of dark matter is always subthermal, so we don't get problems with delta NF. But still, there's an issue if dark matter becomes smaller than a few keV. And that's due to structure formation. So basically, free streaming length in all kinds of scenarios that produce dark matter from the thermal bath, so freeze-in, pandemic production, these kind of scenarios. So it depends on the exact bound depends on the production mechanism, but it's always order a few keV, because otherwise you would get too large constraints from Lyman alpha. So this is excluded for dark matter produced from a thermal bath. Due to a too large free streaming length. Or more generally, Lyman alpha observations, small scale structure observations. It could be either the free streaming length or the sound horizon. Okay, so this is specific to all the kinds of mechanisms that we've talked about so far. But then actually it turns out that very close to this bound, there's a much more general bound that is completely independent of the production mechanism. And this is something like that. So let's say 0.121, depends a bit on how you calculate this. This is a bound that has been derived actually just before these warm dark matter bounds were known. It's a bound that goes under the name of, or is connected to the names of Bringmann and Gunn. And it just comes from the fact that if you have fermionic dark matter, yeah, and you want to explain the existence of dwarf galaxies, yeah, dark matter cannot be too light because you cannot press fermions arbitrarily dense together, because at some point all the phase space will be occupied already. Some from phase space density. Fermionic dark matter. So this is an excluded by, just as the others. Fermionic dark matter in dwarf spheroidal galaxies. Yeah. Okay, but that means that once we don't restrict ourselves to specific production mechanisms anymore, so we remain agnostic about this, then there's actually, essentially no bound for bosonic dark matter. So bosonic dark matter can be as light as you wish, almost. Yeah, and this is one of the main motivations to consider non-thermal production mechanisms. So this is more or less unconstrained, but only for non-thermal production. Yeah, so, but then you should be aware, again, just to provide context, that as you go down in the dark matter mass, of course, you increase the number density because what we have measured is an energy density. So that's the fixed observational input. Yeah, so that means that as we go down in number, in mass, we increase the number density. So these are actually very high occupation numbers. So at some point, one shouldn't really think of these as particles anymore. Yeah, so with very high occupation numbers, it's more adequate to think of very light dark matter as fields. So a very high number density. Means that these are more fields than particles. Yeah, so just to provide again context, so you know that the CMB photons that we observe, there are roughly like 400 or so per cubic centimeter. Yeah, while for the dark matter density is about a keV per cubic centimeter. So that means that this is about like the dark matter mass per keV to the -1 in centimeter cubed. Yeah, so note that this is the density that we have in cosmology, so the average density of dark matter in the entire universe. Yeah, so if you think about the dark matter density in the galaxy, for example, this is rather the scale, the energy scale of GeV per cubic centimeter, so about a factor of 10 to the 6 larger. Yeah, so this is, what I mean by this is really the cosmological number density. So that means that as you go below keV, or significantly below keV, you will have significantly more dark matter particles than even CMB photons. Okay, so let's start to look at specific mechanisms. And the one that is most often discussed goes under the name of misalignment. Yeah, and this one refers explicitly to this kind of situation. Yeah, so bosonic, very light particles or fields. So in other words, we want to consider a scalar field. So we have the Lagrangian. And, well, then you can derive the equations of motion. Of course, you know that in flat space, this is just the Klein-Gordon equation. in curved spacetime, you also get the Klein-Gordon equation. You just have to calculate the D'Alembert with respect to the full metric, in this case the Friedmann-Robertson-Walker metric, and not the flat space metric. So plus the derivative of the potential vanishes, and well, we can calculate this. So this takes basically this form. So again, we get a factor that we can relate to the expansion of the universe. It's the same dilution factor as in the Boltzmann equation. Then there's a gradient term. And the derivative of the potential. Okay, so this gradient term here, so this will, I mean, when you go to Fourier space, this will basically become a k squared a to the minus 2. So for each mode that we have, this means that this will just redshift away very quickly. So even if we start with some large gradients in the fields, this will just redshift away and not contribute to the total energy density, and hence the equation of motion. So hence we will neglect this here in the discussion. But I should mention that, I mean, it doesn't mean that you can always neglect this. So in order to understand like the average density and how it evolves and why this kind of particle or field actually can be thought of as a good dark matter candidate, then it works perfectly on average. But if you actually want to study the evolution of structures, perturbations for these kind of light fields, then you need to take this into account. So in particular, when you study the clustering of these fields at the smallest scales. So there's something that is known as axion mini clusters. So axions tend, or these kind of light fields, tend to form extremely dense structures at very small scales. And that's something that you cannot understand if you throw away these terms, basically because then you have extremely large gradients. Okay. So then let's consider a very simple potential. So just the mass term. And we want to consider a situation where the mass is not constant, but changes in time or by temperature. So specifically, what you typically have is that, I mean, think, for example, of a phase transition, where the mass is essentially 0 at very early times, and then at some point the field acquires a mass that is non-zero. And we want to study what happens in such a situation. So that means we start basically at early times. So temperature is larger than some critical temperature Tc that you can associate to some phase transition. We have something what you can call a slow roll phase, just like in inflation. So basically the mass term is 0, meaning that we have just this condition. So in practice, in most models, the mass term is actually 0. Okay, so what does that mean in the equation of motion? Well, we just have these terms. And then you can directly solve this. So phi dot just scales like a to minus 3. And that tells you that whatever you have in terms of initial velocities, this will quickly be driven to 0. So very quickly we will just have a constant field. Yes? Yes, yes, exactly.
Yeah, but as I mentioned before, you are considering this limit at late times, but at early times shouldn't be considered.
Well, it depends on when you start to consider your equations, right? I mean, I'm just saying that if the mass term vanishes, then both this one will just decay away and the contribution from the kinetic terms will decay away. So you will quickly be driven towards a constant solution. I mean, of course, there will be, like, if you really start with large gradients, there will be a certain, like, an intermediate period or an initial period where you can't do this, but relatively soon, I mean, this is the only solution to the equations of motion. This is just, I'm just trying to motivate why this is my initial condition for a vanishing mass term in the potential.
You cannot have therefore any kind of homogeneous here.
You can, of course, but it will just very quickly decay and give you something like that. Yeah? Unless, of course, you go to like a nonlinear evolution, unless you, I mean, okay, so if you have large inhomogeneities, then this equality is wrong, yeah, because then you don't have Friedmann, Robson, Walker anymore. You have to include perturbations, and once you get into the nonlinear regime, all this argument breaks down. Yeah, but like as long as you're in the homogeneous regime, at least as long as you have sort of a background evolution that is Friedmann, Robson, Walker, then you will get a constant field. Okay, so then, I mean, this is essentially the same that happens in inflation, right? So also during inflation, this is why I call this slow roll, though typically it's not called slow roll in this context. So the only difference to inflation is that inflation is actually, I mean, the energy density of the inflaton is the one that drives the Hubble rate. Yeah, so here we have in mind a field that has only a very small contribution to the total energy density and therefore does not affect the Hubble rate. Yeah? Okay, so then we can consider late times. Yeah, so once we get below this critical temperature, then, well, the new thing, I mean, for example, a phase transition, then we have a field, a mass term for the field. So our equation of motion then is really given like that. Yeah, and you should keep in mind that in principle this is, I mean, typically a mass term that can also involve in time or temperature. But we will consider a situation where this mass term, I mean, it might well appear suddenly around this critical temperature, so as for a phase transition, but then afterwards it will evolve only slowly, adiabatically in time compared to the expansion rate. So let's continue here. So assumption m of t only changes adiabatically. Yeah, which is just what I mean, that we can basically separate time scales, variation scales, and of course in such a situation you typically solve differential equations by using the WKB ansatz. Yeah, so in other words, we make an ansatz where we describe this field as some, well, basically an oscillation with a slowly varying amplitude. Yeah, so this here, by this ansatz, is the slowly varying amplitude, and this is a highly, a strongly fluctuating phase. And then we can use this ansatz in the differential equation here. And well, we actually get two equations. We should better get two equations because we have two free functions here. And why is that? Because, well, everything is real here in this ansatz. So the field is real and A and theta are real. But this is a real equation. But if we take derivatives, we will get both a real and an imaginary part. So that means we get two equations. So the first equation This is just the real part. You see that, from this one here, you take the second derivative. The only real parts that you will get is the second derivative on a, or the second derivative acting on the exponential. Because if you take the cross terms, you will get one term of the I theta down from the exponential, and it will give you an imaginary contribution. So that means that this real part, just write the result, you can write as the second derivative of a, and I divide everything by a in order to bring it into nicer form. Then we get this term here. Also here, of course, it's only the first derivative acting on this one that will give a real contribution. Then this is what I mentioned, the second derivative acting on the potential, plus m squared is equal to 0. Okay, so then by our ansatz, by the WKB method, this one is much smaller. These are the time scales at which a varies, and therefore the time derivatives must be much smaller than the time derivative on the theta. So that means that basically the solution here is just that phi dot is plus or minus m. Remember, m is a function of time or temperature, so I can directly integrate this to get the evolution of the phase as a function of the mass. As a function of time, sorry. Okay, and then I have my second equation. So that's from the imaginary part. So here I get an a dot plus a half 3h plus the double dot over phi dot. And then if I use what I just learned, this here is just the same ratio for the masses. So this is a dot plus a half, and then, or let me even write it like this, and you can see the solution easier. So this is the 3 half h plus 3 half m dot over m. Remember that h is just an a dot over a. So you see immediately the solution to this equation. You need to make sure that a dot, when you take the time derivative, that this cancels this contribution. So that means that a must be proportional to a to the minus 3 half. Then we will cancel this term, and proportional to m. Sorry, this is not 3 half here. It's just 1 half. And m to the minus 1 half to cancel this term. So that is our general solution. And then we can plug it back into the ansatz for the solution. So our field will evolve. We just keep the real part of this here. I just lost my microphone. Okay. So then, well, we just have some normalization constant, and our a of t, let me write the time dependence explicitly, m of t minus 1 half, and then the oscillations. So we need to integrate from tc to the time where we consider this over m of t. So again, this here describes a very fast oscillation, and this is slowly varying amplitude of these fluctuations. Okay, so basically the picture that we have is if this is the field, potential, then you have some kind of general potential, but close to the bottom, to the minimum of the potential, we will of course always be able to make this Taylor expansion. Yeah? So it's basically just the mass term that contributes. So we have a scalar field that rapidly oscillates in this potential close to the minimum. Yeah, that's what's described by this term. And this amplitude describes that the potential, so the curvature of the potential, will change in time, but much more slowly than the actual oscillations. So then the question is, what's the energy density contained in this kind of configuration? So then we just, well, the energy density is the 0,0 component of the stress energy tensor. Yeah, so you know how to calculate the stress energy tensor just using Noether's theorem from the Lagrangian. So if you plug that in, you will find for a scalar field that there's a kinetic term. This is the kinetic energy. There's a term connected to shear in the field and the potential. Yeah, but we already said that this will be quickly decaying away, so we don't take that into account. And then, since we are close to the minimum, it's only the mass term that contributes. So this is essentially the kinetic energy plus the mass term, the potential energy. Okay, so then, well, we have these two epochs. So for T larger than the critical temperature, we have a constant field, so this doesn't contribute. So we just have a constant energy density. For T smaller, the critical temperature on the other hand, then we just need to use this general solution that we just found. So we get a c squared, and then we have an 1/2 a to the minus 3 m to the minus 1. And then we get, well, from the mass term, we can just get a cosine squared of this expression here, so integral over m. And then for this term here, you have to again keep in mind that this is the fast oscillating part. So when you take a derivative, you will get a much larger contribution from taking derivative on this part of the solution than from this part of the solution. So you basically just take the derivative on this one and get one factor of the mass. So the cosine becomes a sine, and then you get one factor of the mass in front of this, you square it. So this is just approximately equal. We throw away the slowly varying solution. So we have a plus m squared sine squared. And then you see, of course, well, cosine squared plus sine squared, so we can nicely simplify this. And we can also use the fact that, of course, energy must be conserved. So at the transition point, we can use this to fix this integration constant here, c. Because then we must have the same energy densities there. So finally, we find that this is m at the transition point, so when, like, right after the phase transition. Like this. Okay, good. So then we can further get rid of this AC here, because this is just related to the Hubble expansion rate. So the mass in particular Yeah, that by our assumption should be the same as the Hubble expansion rate. Yeah, so this is what marked the transition. But then the Hubble expansion rate is just given something we've used many times now. Yeah, so it's just the temperature, we're still in radiation domination, divided by the Planck mass, temperature squared divided by Planck mass. So this is proportional to this scale factor to the -2. Yeah, so that's how you can get rid of the scale factor. And from this expression then numerically derive the density that we have today by setting the scale factor A to 1. And you find that this is in units of what we want to have for the cosmological dark matter density, so keV per cubic centimeter. Then you need the mass today. Yeah, so this is a slowly evolving mass and time. So this is the mass that the field has today in EV. And then there's a ratio of the mass today to the critical mass, or the mass at the phase transition. And then we have the field value, the initial field value, in units of 10 to 11 GeV. Yeah, so from this, we can see that in order to get the observed dark matter density, we need like extremely large initial field values. Yeah, or we could sort of slightly compensate for this by very large ratios here. Okay, so then, I mean, this still looks a bit strange, yeah, because we have, well, we're talking about a field, yeah, so how do we know that this is actually dark matter? Yeah, I mean, we get some indication from the scaling here. Yeah, so if this is a slowly varying mass term, yeah, and in particular, if we require that this m0 is, I mean, actually the same value more or less as the time of equality, so that's when we start to measure the impact of dark matter, yeah, then at least we know that the energy density actually scales like the energy density of cold dark matter. Yeah, so that's already a good sign. So to follow up on that, we should consider the pressure of this field. Yeah, so then we just look at the space components of the stress energy tensor. And then you find that this is, well, again, a kinetic contribution, but then minus the potential contribution. Yeah, so in our case, this is just the mass term again. Yeah, so that means we have exactly the same calculation. So for t larger than or smaller than the phase transition, what do we find? We find exactly this one here. So the pressure is c squared 1/2 a minus 3, and then a cosine squared minus sine squared. Yeah, so what does that mean? Well, remember that these are very quickly oscillating terms. Yeah, so what we really want to calculate is the average pressure. Yeah, and then these two terms contribute exactly the same. So the average pressure that contributes to the to how this field behaves is actually 0. Yeah, and that's really the basis for why we would call such a field, or why such a field takes more or less the same form or behaves the same way as just non-interacting vanilla cold dark matter. Yeah, so it has the same a to the minus 3 decrease of the energy density and is pressureless. Okay, so then I said just in passing that this is a nice behavior, but we should really make sure that it's, very well satisfied, at least during meta domination. So whenever anything to do with structure formation or even CMB anisotropies comes into play. Yeah, so roughly you can then require that the mass is constant starting from the time of equality. So this is like cold dark matter if this time of the phase transition. Okay, so the temperature of the phase transition should be much larger than the temperature of equality. Yeah, so basically the phase transition must happen before, because afterwards, if it happens later, then we don't get this solution here. And that is the same as saying that the mass at the phase transition should be larger than about 10 to the minus 27 electron volts. Yeah, so that's what I meant, or what I had in mind when I said that there's basically no constraint on the mass of bosonic particles or fields. You know, that if you have a concrete production mechanism, you have to make sure that it actually looks like cold dark. Yeah, and in this kind of mechanism here, it only does so if it is larger than this mass scale. But this is, of course, a super small mass scale. Yeah, remember that we have occupation numbers of about 1 per cubic centimeter for keV, and this is 10 to the minus 27. Okay, so why is this called misalignment? Misalignment mechanism, because we start from this initial displacement in the potential. Yeah, so we start somewhere here, yeah, some small displacement from the actual minimum. Yeah, and then the oscillations that start once you actually have a potential in non-vanishing mass terms. So initially the mass term vanishes, so we start somewhere. Yeah, and then just because a potential appears, yeah, the result is something, a field that behaves for all practical purposes like cold dark matter. Okay, so then there are basically two independent situations that one can consider that are interesting about this initial displacement or misalignment. Yeah, so one is that this transition here happens, I'm confused with my t's, like capital and small t's. Yeah, so it happens before inflation. Yeah, so small t is smaller, large t is larger. Yeah, so what does that mean? Yeah, we have some phase transition. Yeah, so the field starts to oscillate, behave as cold dark matter, and then inflation happens. Yeah, so that means that, or no, sorry, the field initially has some displacement, yeah, in some patch of the universe, and then inflation happens. Yeah, so that means that this patch of the universe, where we have a given value of the initial misalignment, is blown up to make up the entire universe. Yeah, so that means that basically this phi I here is just an input parameter to this entire discussion that we cannot determine. Yeah, it's just a free input parameter. So the phi I is an arbitrary initial condition. So an unknown free parameter. On the other hand, if the phase transition happens after inflation, Yeah, then, I mean, of course, inflation produces like scales larger than the size of the horizon at the end of inflation. And in all these different patches, like outside the horizon, that are not causally connected then afterwards anymore, you can have, like when this phase transition happens, this initial field here, then the initial misalignment can have different values. Yeah, so then the universe expands, the Hubble horizon expands. So as the Hubble horizon expands, all these different patches will come into the horizon, but with different values of phi I. And if this happens at a very small scale, it means that basically what you observe inside the horizon, you should average over all possible configuration of this initial misalignment phi I. So that means that our phi I squared here, which we use to normalize the initial fluctuations, the density, you should replace by an average over all the phi I squares. And of course, if you do this, you have to say something about how the potential looks like. If this is a periodic potential, this is basically, I mean, the averaging. You can parameterize this field phi here. It's actually for a periodic potential. You can parameterize this field such that it's just given by an angle, so from 0 to 2 pi, and then you average from 0 to 2 pi. And then you find pi squared third times some mass scale. So remember that this is a scalar field. Of course, when I said that you can parameterize this with just an angle, you make the field dimensionless, so it must be connected to some mass scale, and this mass scale is the mass scale of the symmetry breaking. So this is for periodic potentials. So that means that in order to get the correct Rayleigh density, we have actually a well-defined constant from this calculation times the mass of the field divided by this mass scale. And such a theory is very predictive, because you have, I mean, this constant you can calculate, and then there's, I mean, depending on the model, or well, you can of course reabsorb part of the constant in this dimension full scale here. But there's the scaling linear in the mass, and inversely quadratic to the scale at which the phase transition happens. So for a concrete model where you know how to calculate the phase transition, you know exactly what to do here, and then in principle for each mass you get exactly one value of the dark matter density today. Okay, so I guess we take a short break and then continue in 10 minutes, so 10 past. Okay, we can slowly start again. So first of all, there's of course a -1 here in the mass dimension. So a scalar field has mass dimension 1. So if I introduce this with a minus here, there's a -1 there. So this was noted by several people. Okay, good. So what we have learned is just that there's like a very generic way of producing something that, for all practical purpose, is behaves like dust, like a cold dark matter fluid, even though from the ansatz it's really not something that you would think of in some sense as a particle. It's more like a field, so very, very light particles with very large occupation numbers. And that of course also has impacts on structure formation actually. So I said that, I mean, just in passing or very sort of quickly, that okay, we have no pressure, we have an energy density that goes like h to the -3. So that means naively and at the zero order level, everything is fine. Yeah, but you should really check perturbations before you can be sure that this is actually, would actually reproduce observations. Yeah, and this is a non-trivial task. And the answer is A, yes, it does. And B, there are actually small differences to ordinary just cold dark matter particles that you could potentially test. Yeah, and there's some discussion going on, and it's also like numerical simulations or structure formation with these kind of light fields are just not at the same level, are not as advanced as in the case of cold dark matter simulations, particle simulations. Yeah, so this is something one should keep in mind. So there might be potential signatures here still hidden. So let me finish this discussion by talking very briefly about model classes where this can be relevant. Yeah, so the first one, and that's the most often discussed in this context, are ALPS. Yeah, so axion-like particles, which of course includes the axion itself. So these are light particles that are typically, in particle physics, when you think about light particles or even massless, you think about Goldstone's theorem. Yeah, so these are Goldstone bosons or would-be Goldstone bosons, so they get an extremely small mass. And the characteristic thing about Goldstone bosons is that they are connected with a shift symmetry. Yeah, so that means they have like derivative couplings. Yeah, so when you change the field by a constant, the Lagrangian doesn't change. And that is why it's very typical that you have, if you have a shift symmetry, yeah, it's very typical that you associate, in the original theory, before you have a symmetry breaking, it's very typical or natural that you associate periodic potentials. Yeah, so that's sort of the broken version of this shift symmetry. Then you still have a shift symmetry only by discrete amounts. Yeah, so that's a very typical thing to get. So then you have this kind of periodic potential that I mentioned. Yeah, so phi c here is the field value connected to the scale of symmetry breaking. So what that means, if you have only shift symmetry, then importantly for phenomenology is that you get a coupling to the photon field. Yeah, so FF dual, this is the ordinary electromagnetic field tensor. So this is essentially, in terms of physical fields, just the scalar product of electric and magnetic field. And that's the basis for experimentally searching for these kind of particles. So it's basically, it's referred to as axion-photon conversion. So you have you can apply external fields, electromagnetic fields, for example, in cavities, and then use this coupling to convert axions to photons and try to detect them. This is how people look for this. So for example, in this model class, there's the QCD axion. And well, that is characterized by a coupling to the, in the QCD sector, to the gluon field. Yeah, and that's basically this is the model-independent way, if you wish, how to introduce the QCD axion. So the reason is that, so this is the axion field here, A, right? And if you just think of this as a constant, yeah, the strong CP problem states that, well, why don't we have this kind of term in the QCD Lagrangian? Yeah, so there's nothing that would forbid this, this kind of term, GG dual, G is the gluon field strength tensor, but still we don't have it observationally. Yeah, and then the Pecci-Quinn solution to this problem is a dynamic solution. Yeah, so observationally this is just a very small value. Yeah, and the dynamic solution is to actually couple this to a field. Yeah, and then say that if you have a symmetry like this one, then you can dynamically understand why this field is very small, and understand why the observed value of this coupling is extremely small, if existent at all. But then, of course, in general, there's also a coupling of the axion to quarks. Of course, with the shift symmetry. And this is somewhat model dependent. It depends on how many quarks you introduce and how many quarks the axion couples to. So this kind of introduces the axion, the QCD axion, to solve the QCD problem, the strong QCD problem. But this is basically a somewhat model-dependent way of fully implementing this in a model. But anyway, the options that you have here are rather limited, meaning that in order to satisfy the experimental bounds, you basically fix the decay constant. And if on top of that you also want to have the correct relic density, you need this one. So you basically, what I'm saying is that you basically fix the relation between this, the decay constant and the mass of the axion. And then you find that this is roughly 10 to the minus 5 electron volt. So this is the only way a QCD axion could provide the correct relic density. And this is much, much smaller than the electroweak scale, which was the original hope when people introduced the QCD axion as a solution to the strong CP problem. So then we can get back to what does it mean to talk about ALPS. Then you have a much larger model building degree of freedom. You basically don't care about these things here. You just write it in a phenomenological way. You just postulate that there's some kind of particle that couples to photons like that and is produced via misalignment. And then the range is slightly larger. So that is currently something between 10 to the minus 6 and 10 to the minus 3 electron volts. And then you can phonologically search for these and try to exclude the range that gives the correct relic density. Okay, so the other model class are hidden photons. So you add some U1 prime, so a new U1 symmetry. And, of course, it must be a photon, right? And then if it's a U1, there's a natural connection to the standard model by kinetic mixing. So if this is the standard electromagnetic or also U1 field strength tensor of the standard model, then you have this kinetic mixing term that is gauge invariant. That only works for U1s, otherwise not. And that, of course, gives you an experimental way to test this. So you can produce these dark photons and then look for basically this interaction and try to look for hidden photon conversion in all kinds of both lab experiments and astrophysically. So that's how you can search for this. Okay. So now to something completely different. We are discussing non-thermal production mechanisms. And the next thing I want to discuss is what is known as gravitational production. So typically this is the kind of thing that is relevant at the end of inflation. You know that during inflation, of course, the inflaton produces density fluctuations that then get into the horizon again. And somehow this is converted to ordinary matter during during reheating. And this is a way of producing dark matter as well. And then, of course, the simplest way to think of this is that you have, for example, the inflaton directly decaying to dark matter. This is kind of the boring way. It would basically be a Boltzmann description. You just write down a collision term, and of course, you can just postulate that there's a direct coupling between the inflaton and dark matter. And then you get into, you have to answer questions like, okay, why does like a Planck scale particle have like order 1 coupling to maybe a GeV particle or so that you want to have to describe dark matter? It's a model building question. So what I want to discuss here is sort of like a completely orthogonal situation where there's no like particle physics type of coupling at all. So you would naively say then, okay, how can you then produce dark matter? And the point is, of course, that it's not possible to have no coupling. You always have gravitational coupling. So just by having 2 different fields in the Lagrangian, in a non-flat background, there will be a gravitational coupling. So gravity always couples everything. Nothing is, there's nothing that is neutral under gravity. And that's the kind of thing I want to discuss here. So for that, we need to do a little bit of basics about studying QFT and curved space, or space-time. So, basically, if you think about just how GR is introduced, there's this principle of minimal coupling. So that means that if you have a theory in Minkowski space, whatever complicated theory, your favorite particle model, you just replace the partial derivatives with covariant derivatives, and you replace the Minkowski metric with the general spacetime metric, and then automatically the effect of gravity is included. So what sounds like a very complicated task, right? Maxwell's equations, including nonlinear gravitational effects, is actually very, very simple, just by this prescription. So that's one of the beauties of GR. Okay, but of course this is a classical in the sense of not quantum discussion. So in QFT, what are particles? They want to describe particles. So particles, what are they? Well, in some sense, they are representations of this thing here. So representations of Poincare symmetry. So are representations of the Poincare group. And that should immediately tell you that, this thing here is tough, right? So like what should you do? When you go to an arbitrary curved space-time, how do you even think of particles? It's completely unclear. So let's look at this for a simple example, so just a scalar field. So a free scalar field. So then in Minkowski space, this is the Klein-Gordon equation. So the box is evaluated with respect to the Minkowski metric. And then, of course, you know the solutions to this. These are just free plane waves, right? So ikx plus, and then the point is that these positive frequency solutions come with the annihilation operator, and negative frequency solutions come with the creation operator. And this is one of the nicest results in quantum field theory in a nutshell, because it sort of beautifully demonstrates the particle-wave duality in quantum mechanics. You have mode functions that are simply solutions to the wave equation, to the equation of motion. So that's why these things are waves. Yeah, but of course, the whole thing is an operator. And in this basis here, it's this Fock space construction. So you produce individual quanta field excitations of the vacuum with specific momenta k and energies that satisfy the relativistic energy momentum dispersion. So that basically, in a nutshell, means that in this basis here, you define the vacuum by saying that, well, it's the state that is annihilated by all these operators. Yeah, and we define one particle states by some proportionality constant, and we want to normalize them appropriately, acting on the vacuum. Okay, but in this discussion, it's really crucial to distinguish these two, right? I mean, one annihilates the vacuum, the other one creates particles from the vacuum. So how do we distinguish A and A dagger in a general basis? Well, I mean, the point is that you need to distinguish between this one and this one. So you need to distinguish between positive and negative frequencies. But we can only do that if, I mean, in more general terms, there is a time-like killing vector in our space-time. So in other words, if the metric, if space-time is not explicitly time-dependent, like in Minkowski space, for example. So we need a time-like killing vector to distinguish positive and negative frequency modes. Yeah, so how do we do that? Well, I mean, if there is a time-like killing vector, then there's always a coordinate system in which it takes the form of just the partial derivative in this coordinate direction. And then we distinguish positive and negative frequencies by saying that, okay, with acting with this vector on our mode, that gives me a plus or minus, well, okay, a minus for the positive frequencies and a plus for the negative frequencies, I omega, okay, let's use this same notation here. Yeah, so the frequency is an eigenstate of the killing vector. So for omega k larger than 0. But if there is no time-like killing vector, you can't use that. So there's no intrinsic way of telling what is a negative frequency, what is a positive frequency. And therefore, there's no intrinsic way of saying what is A dagger. There's no intrinsic way of saying what is a particle. Okay, so let's write this up in a bit more detail. So in general, if we don't have Minkowski space, then we still have the Klein-Gordon equation, just with an arbitrary metric. And then we can still decompose this in Fourier modes. So we can introduce Fourier modes like this. So separate out just the spatial part. So we do a Fourier transform with respect to the spatial parts. So that means that for each of the case, for each of the modes, we just have a time-dependent function. And then we would write our, making this an operator just means that we write this as some kind of mode function times an operator A. And then, since this has to be a real field, or this is a real field, this is then a real valued operator, this must be of this form. So in other words, in this decomposition here, I mean, by analogy to what we did here, this U is the would-be positive frequency mode. Yeah, then it matches with this. But of course, since we don't have in general a time-like killing vector, yeah, so in general, space-time can be time-dependent, there's nothing that tells us that we should use these modes. Yeah, so nothing that tells us that we just should use modes like that or any modes that are related to these ones here with Lorentz transformations. Yeah, so we can just use any other modes. So let's call them V. Yeah, and then I call the operator B rather than A. No. And okay, so then the question is how can I relate them? Well, in this way of writing this, yeah, I should make sure that these modes here, the U's and V's, are orthonormalized. Yeah, so basically I should make sure that, okay, let me write it in a discrete form. This is the normalization I choose for my modes, yeah, such that I really have a complete set of modes, so a complete set of solutions to the Klein-Gordon equation. Yeah, in general, these will be much more complicated solutions than just plain waves, but by definition, they will be solutions to the Klein-Gordon equation, and they will form a complete set. Yeah, so this scalar product here, in case you haven't seen this, is defined with respect to it's an integral, and then you have a ui and the derivative acting on both sides, something like this. Yeah, so you construct the scalar product such that it is conserved under the Klein-Gordon equation, because otherwise it's not a meaningful definition of a scalar product. So that's what you should have to use. So just in case you wonder what I mean by this for an arbitrary solution. Okay, but then I can use this normalization to write these new modes in terms of the other modes. Yeah, so just since I know that this is a complete set, a complete orthonormal set, this is a complete orthonormal set, I must be able to write these just as linear combinations of these. So that means that I can, let's call these coefficients alpha and beta. Yeah, and these coefficients are known as Bogoliubov coefficients. Okay. And then you can use this description here to basically, there's an equality here, right? So you can basically solve for the B's and B daggers and express the B's and B daggers in terms of these coefficients. And this then takes the following form. So this is an alpha conjugate minus beta conjugate and a minus beta and an alpha. Yeah, so that is just mathematically what I said before in words, that there's no way for us to distinguish annihilation and creation operators. Yeah, so just by choosing a different set of basis functions, I will redefine what I mean by annihilation and creation operators. Okay, so let's check what that means. Yeah, so for example, let's say that we start in a vacuum state. Yeah, but then of course we have to say vacuum state with respect to what. So let's say that for some reason you have chosen to use these mode decompositions here. And then of course the vacuum state is defined by all the A's acting on the vacuum state giving 0. So vacuum with respect to UK. Then all the A's annihilated and I should add a subscript U here to distinguish it from other possible definitions of the vacuum. But then I can use this very state and ask what an observer that decides to use these modes here instead sees. So in particular, I can calculate the particle number with respect to Vk. So that would be the number in this other frame. And well, I insist on using this quantum state. The quantum state does not change. And then the number operator in this new frame, or in this frame defined by the mode functions V, is just a B dagger B. And then you see that, well, I mean, in order to evaluate this expression, you need to use this here. So you express the B as a linear combination of A and A dagger. So you see that B is A conjugate times A. A acting on the vacuum will give 0, so this doesn't contribute. But then there's a contribution from minus B conjugate A dagger. This will survive the vacuum. And the same here, the B dagger, you write as minus beta Ka. That's actually a term that survives, while the other one does not survive. So what we find is that this is beta K squared. And that in general is not 0. In a Minkowski space, it will be 0. In a general space, it will not. So that means that what we would say with all, I mean, we have very good reason to say that, okay, this is our vacuum. I didn't change anything. I just implemented minimal coupling, as always. I start with a vacuum state. Everything should be fine. And then you find, no, it's not. So we produce particles. So in practice, and that's, I mean, I don't think, I guess we will discuss this tomorrow. Tomorrow I want to show you an explicit example, but this will be a bit technical, so I guess we should wait until tomorrow. So the typical application is that you basically start with something that looks like a Minkowski space. So you basically choose your mode functions, U, such that they are exactly these modes. And that can be because you are actually considering a space-time that is asymptotically flat. Then you don't have much choice. Or you can use, of course, the GR argument that whatever I do, locally, I can always choose coordinates such that I have flat space-time. So you can actually always choose these modes to take exactly this form. And then the next step is to say that, okay, these modes V, they should just be a fully general solution of this Klein-Gordon equation. And since it's a complete set, you can, of course, always express them in terms of these modes. So that means that very practically, you would define the vacuum in this way with your standard way of defining vacuum, as you learn about this in quantum field theory, just locally, 0 particles. But then, because you look at the complicated solution of the Klein-Gordon equations, you will have a beta that is a function of time. Beta squared is not 0, so you actually produce particles as a function of time. Okay, so tomorrow we will look at a very concrete example, very, very simple. We just say that, okay, let's assume that the entire universe is just made by the inflaton. So we have a scalar field plus a potential. And then on top of that, we add another free scalar field, exactly of this type. So no explicit coupling, and then study what happens. And also try to reconnect this to our previous understanding that a particle production should have something to do with a Boltzmann kind of thing. So you would expect to be able to describe this as a scattering process. So in that case, you would argue that, okay, so why should I do all these complicated things? I mean, what I can think of is if we have the inflaton like this, Yeah, then we have the graviton, H, and that produces some scalar field chi. Yeah, so surely what you're telling us now is nothing but this, just in a very complicated language. Yeah, and tomorrow we will see that this intuition is actually correct, but only in a very specific limit of parameter space. Yeah. Okay, see you tomorrow.